Hello guys, so as you may know, I have previously made a video on a collisions detection system, but let's say that system is rather inefficient and very shitty. So today I'm gonna remake it using a very well-known method in video games, which is called Separating Axis Theorem.
Nice.
So first of all, let's go over what the Separating Axis Theorem is. Well, the separating axis theorem is a method well known in terms of overlap or collision detection, especially in video games. And it states that if there exists an axis onto which the projection of two polygons do not overlap, the two polygons are separated. So take a look at this example here, where two rectangles are projected onto two axes, x and y, which is the maximum number of axes onto which a triangle can be projected. We'll go into that more later. So as you can see, on both of the axes onto which the rectangles are projected, there is no separation whatsoever between the projections. Therefore, the two objects can be marked as overlapping. Here's another example. Here you can see the rectangles are separated visually, and when it happens, although the projection onto the y-axis of the two triangles overlap, the projection onto the x-axis exists separation. With just one separation from one axis, we can conclude that the two objects do not overlap. So before we get into coding, there are often two popular questions. First is, how do you determine the axis onto which the polygons must be projected? And two, how do you project the polygon onto a line? So first of all, the axis onto which you must project the polygons are determined by the normal vector of each edge of the polygon. And to project it onto an axis, you simply take the maximum and minimum dot product of each of the vertices of the polygon with the axis. Note that the axis must be a normalized vector. And in 3D space, the separating axis theorem is still the same, but with the difference that the axis onto which the shapes must be projected extends to the cross product of each of the face normals of one polyhedra with each of the face normals of the other polyhedra. So enough of talking, let us get into programming it. So the first thing to do here is to get the model meshes of each of the game objects, which we will use to get the vertices, which store the normal vectors and the coordinates necessary for projection. And then comes projecting the shape onto each of the axes, which is done by getting the dot product between the axis and each of the vertices. The two ends of the projection is the minimum and the maximum value. After which, if no separation is found, then we will have another set of axes, which is formed by the cross product of each of the face normals of one object with each of the face normals of the other. And If still no separation is found, then the function eventually returns true, as in collision detected. And now we connect the function with the rest of the game engine's collision detection system. Now it's time to run the code, and as you can see, it's running very slowly. I've had it print the delta time, and as you can see, it's atrocious, taking 1 second to render one frame. Okay, I've tried to render just a simple box, but it's just like a slideshow. I guess optimization is imperative. So one of my methods of optimization is to preload all the face normals of the object beforehand. This way, in the SAT function, we would only have to retrieve the vectors and then transform them. This also helps us eliminate excessive normal vectors, thus proving conducive to the performance. Okay, it's time to run the code, and it's much smoother now. Cool! So another way is to implement axis-aligned hitbox. Forming a normal matrix may be very resource intensive, so we would try to minimize that as much as possible. And now it is solidly smoother. I would recommend using an axis-aligned hitbox for a stationary object. So another one of my methods of optimization is what I would call the close proximity check. So each object will be surrounded by an imaginary sphere whose radius is defined by the maximum distance from the center of the object to the farthest vertices. So as we can see here, the distance from the center of the sphere of this object to that of this object with the radius R2 is larger than R1 plus R2. So the objects are clearly apart from each other, and the separating axis theorem check can be skipped, saving a lot of performance for when there are multiple objects. Okay, with everything being clear, let's now program it. And now it certainly feels better, but the real effect will only be tangible when there are a lot of objects.